Hello, we're the Solar Nano Boost team, and this is our set presentation. So what is the problem? Inherent limitations of the photon-to-current conversion process leads to the lower efficiency in solar cells. The main problem is the mismatch between the solar spectrum and the optical responsivity profile of the silicon-based solar cells. As we can see, the red region isn't properly utilized because of thermalization loss and non-absorption of the low-energy photons. So what is the solution? We are currently working on a nanostructured material coating that can shift the incoming spectral regions. As we can see, when the solar cell is exposed to solar radiation, it can only process the visible parts of the spectrum. Once we apply the coating, however, the coating will shift the input ultraviolet and infrared into visible that can be effectively utilized by the cell. Here, we demonstrate a prototype that we've been working on. Using an optical fiber spectrometer, with the UV light, UV emission is detected as a control. But when we shine a UV light on the nanomaterial in powder form, we see the emission lines in the red wavelength region that possibly demonstrate down conversion. Here we have some preliminary data. This was performed at a startup company in the Bay Area that showed current enhancement in the presence of additional UV light on a coated cell. And here we have data from NREL through the Commercialization Assistance Program from some time ago. The blue line shows features of down conversion here and here. Scale of opportunity. We're aiming for this coating to be applied in retrofit. If we can improve the cell performance efficiency by even 5%, our end goal, with just a one-time cost of applying this coating, that would be phenomenal. For example, here we can see the net solar generation in the US over the past 20 years. In 2021, it was closer to 91,000 kilowatt hours. If we can improve it by 5% without any additional solar panels installed, that would go to 95,436 kilowatt hours. With this example, it shows the potential end goal that we hope to get to with this technology and the impact that it can have on the energy market. So what have we done so far? 1. We fabricated material formulation prototype that when exposed to UV light emits light in the red region. 2. We conducted initial outdoor testing with the sun with coated solar cell modules. It's preliminary, but we noticed some improvements in performance in cloudy day settings. 3. We work with D2 Solar from the American Made Network to conduct performance testing on the coating itself. Through that process, we obtained some mixed results and realized we needed to get a better idea of where we want to implement this coating, since a traditional solar cell module contains an anti-reflective coating base layer, which is encased by a glass plate. So with this, you see, we wanted to test out other cases where we move the formulation into a lower level before the anti-reflective coating, and we want to do this testing in the next round. These are some of the next steps that we're currently looking into. One is using the NREL labs for state-of-the-art testing for the PV modules. Another is determination of the optimal placement of the coating on a cell, as mentioned earlier. And then also operating out of a lab to synthesize greater batches of the materials. For the target market, we're considering working with solar cell manufacturers and have done some customer outreach with individual solar panel users that may be interested in this technology. We also are looking into licensing model for moving forward with this technology. Now we'll be showing a demo of this formulation prototype in action with the help of the founder, Dr. Prabhakaran Kunil.
Hi guys, my name is Dr. Prabhakaran Kunil. I'm the founder of Solar Nano Boost. In this presentation, I would like to introduce the measurement system that we have. There are two modules which are similarly prepared and separately connected. The pre-code conditions show that the one on the left side is 0.03 ampere less than the other one, and we decide to code that low performing one. You can see that we use a small pipette to coat the material on the left side panel. The coating takes about 24 hours to cure for the best results. And we can see the coated panel is performing 0.03 ampere better than the uncoated one, which is a net improvement of 0.06 ampere. This is a quick demo given the constraints of this submission. Thank you for listening.